We introduce a new algorithm for online system identification and calibration of dynamic models for autonomous ground vehicles. This algorithm consists of a rolling window which stores last n states of the robot as a motion sample, a priority queue which stores most informative motion samples, and an entropy scoreboard which fairly chooses informative motion samples for the priority queue. Here we assume we want to calibrate two parameters of the dynamic model. Once the state of the system evolves and the rolling window is full, we construct an optimization problem to regress parameters of the dynamic model. Let's say the expected trajectory of the vehicle starting at S0 to be the blue line, but the actual vehicle's trajectory was a little bit off and goes to the right. We define a cost function between expected and measured states of the system and minimize that cost function using Gauss-Newton optimization to get the mean and covariance of the estimate. Then an entropy measure is calculated for each parameter from diagonal of the covariance. Here we show these entropy measures by arrows where red color means high entropy. Later we use green to show lower entropy. Then the motion samples and corresponding entropy measures are pushed in the table. Once an update to the priority queue happens, we construct a new optimization problem to estimate the parameters based on all samples in the queue. As the state of the robot evolves, new rolling candidate estimates are evaluated and added to the queue. Let's assume we require this model to have at least two informative motion samples for each parameter. Now, if a new motion sample comes in which doesn't have a lower entropy compared to what we had in this scoreboard, then that sample is rejected. But if there is a sample which is more informative for both parameters, then it is replaced with the sample which had the highest entropy. Let's say we receive a new motion sample which parameter 1 needs it since it has lower entropy, but parameter 2 already has two samples in the queue which are both better than this sample. As parameter 1 needs this sample, we add it to the queue, and we only count the effect of the lower entropy values, such that both parameter 1 and parameter 2 each have at least two informative samples in the queue. We verify our method by testing it in both simulation environment and also on an actual 1/8 scale four-wheel drive vehicle. We try to estimate tire friction coefficient and wheelbase parameters of the model in both experiments. We are able to reach ground truth solution in simulation tests and an accurate estimate for the actual vehicle tests. Thank you for watching and hope to see you in the poster session.